three things. Three perfectly reasonable, perfectly obvious things that every sane person believes, and I am going to show you that at least one of them is dead wrong. Not probably wrong, not might be wrong if you squint. Mathematically, provably, experimentally wrong. One of these three ideas you carry around in your head every single day that you have never once questioned cannot survive contact with quantum mechanics. And the scary part, we still do not know which one has to go. All right, so let me tell you what the three things are. Number one, when something happens, it really happens. If I drop a glass and it shatters on the floor, that is a real event. The glass broke. That is a fact about the world, not a matter of opinion, not perspective dependent. A real definite thing occurred. Number two, you can make free choices, or at least you can make random ones. If I decide to measure the spin of a particle this way instead of that way, that choice was mine to make. Nobody forced it. Nothing predetermined it. I picked. Number three, what I do here does not instantly change what happens over there. If you are sitting in a laboratory in Tokyo and I am sitting in a laboratory in New York and I flip a switch, that flip does not instantaneously rearrange your equipment. Influences travel at the speed of light at most. Nothing jumps across the universe in zero time. Physicists call this locality. Three beliefs. Every one of them feels as sturdy as a concrete wall. And yet when you push quantum mechanics hard enough, when you take it to its logical extreme, at least one of these walls has to crack. That is the paradox. And the investigation into how we got here and what it means is one of the strangest detective stories in all of physics. Let me start at the beginning. Not the very beginning, but the place where the trouble first became visible. You have probably heard about the double-slit experiment. A particle, let us say a photon, approaches a barrier with two slits. And if you do not check which slit it goes through, you get an interference pattern on the screen behind. Bands of light and dark, like ripples in a pond overlapping. The photon behaves like a wave. It seems to go through both slits at once. But the moment you set up a detector to check which slit the photon actually goes through, the interference pattern vanishes. You just get two clumps. The photon behaves like a particle again. Now I want you to sit with that for a moment, because people hear this and they nod and they move on as if they understood it. You did not understand it. Nobody understands it. What happened is that the act of looking changed what the photon did, not the act of pushing it, not the act of disturbing it with some clumsy instrument. The mere acquisition of information about which path it took changed the physical outcome on the screen. Information and reality got tangled together in a way that has no analog in ordinary life. Before you measure, the photon is in what we call a superposition. It is not going through slit 1, it is not going through slit 2. It is doing some combination of both, and that combination is real, because it produces the interference. The moment you measure, the superposition collapses. The wave of possibilities crunches down into a single fact. One definite outcome appears fine. Weird, but we have been living with this for decades. Or physicists learn to calculate with it. Engineers build lasers and transistors using it. We can handle it, or we think we can. But a fellow named Wigner, a very brilliant physicist, came along and asked a question that nobody had a good answer to. He said, okay, suppose my friend is inside a sealed laboratory. My friend measures the photon. From my friend's perspective, the photon collapses. Done. One definite result. My friend sees it, but I, Wigner, am outside the laboratory. I have not opened the door. I have not looked inside. As far as quantum mechanics is concerned, my friend and the photon are both part of one big quantum system. And until I, the outside observer, make a measurement on the whole laboratory, the equations of quantum mechanics say that system is still in a superposition. My friend, from my perspective, has not gotten a definite result. My friend is entangled with the photon in a haze of possibilities. So who is right? My friend says, I saw a definite outcome. The equations I write down from outside say, no, you are still in superposition. This is not a small disagreement. This is a disagreement about whether a fact about the world has actually occurred. Wigner thought about this and figured, well, consciousness must be special. Once a conscious observer gets involved, the superposition must really collapse. That was his way out. But most physicists did not like that answer because it puts human minds into the equations of physics in a way that seems frankly arbitrary. There is nothing in the mathematics of quantum mechanics that says collapse happens when a brain gets involved. Nothing at all. So we have a puzzle. But for a long time people said, well, this is philosophy. You cannot really test it. It is just a thought experiment about the meaning of quantum mechanics, not a real physical paradox. Interesting, sure. Troubling, maybe. But not something that bites. That is where the next clue comes in, and it comes from a man named John Bell. In 1964, Bell proved something remarkable. He showed that if particles have definite properties before you measure them, and if influences cannot travel faster than light, then there are strict limits on how correlated the measurements of two entangled particles can be. Specific numerical limits. You can calculate them, write them down on paper. They are not approximate. They are exact. The idea is beautifully simple. Imagine two friends, one in New York, one in Tokyo. Each receives a particle from an entangled pair. Each friend independently chooses one of several possible measurements to perform. They record their results. Later they compare notes and look at the correlations between their outcomes. Bell showed that if the particles carried hidden instructions, like a cheat sheet written before they separated, the correlations could only be so strong. No matter how clever the cheat sheet, there is a ceiling, a mathematical boundary that no prearranged scheme can cross. And then the experiments were done, first by John Clauser in the early 1970s, then by Alain Aspect in 1982, with increasing precision each time. And the correlations violated Bell's limits. Nature exceeded what any local predetermined theory could explain. This was not a small violation. Not ambiguous, not borderline. The experiments were clear as a bell, if you will forgive the pun. Something had to give. Either particles do not have definite properties before measurement, or influences can travel faster than light, or something else entirely is going on. Most physicists settled on the first option. Properties are not definite until measured. That is the standard interpretation. Measurement creates the outcome. The particle does not have a spin until you check it, and then it does. All right, so far this is familiar territory if you have spent any time thinking about quantum physics. But I led with three assumptions for a reason, and the real punch has not landed yet. What I have told you so far is the setup, the investigation, the clues spread out on the table. The actual paradox goes deeper, because some very clever people took Bell's idea and Wigner's friend, and they put them together, and what came out the other side was much worse than either one alone. Picture this. Two laboratories far apart. In one laboratory, a physicist named Charlie is doing an experiment on an entangled particle. In the other laboratory, far away, a physicist named Debbie is doing an experiment on the other entangled particle. So far, this sounds like a regular Bell experiment. But there is a twist. Outside Charlie's lab, there is Alice. She has not opened the door. She treats Charlie and his particle as one quantum system. Outside Debbie's lab, there is Bob, doing the same thing. Alice and Bob each get to decide, do I open the door and ask my friend what result they got? Or do I perform a completely different kind of measurement on the whole, sealed laboratory, treating my friend as part of the quantum system? This is the extended Wigner's friend scenario, and it is diabolical, because it combines entanglement between distant particles with the observer problem at each location. When you work through the mathematics, and when you make certain reasonable-sounding choices about how Alice and Bob perform their measurements, quantum mechanics predicts correlations between their results. Correlations you can calculate, and those predicted correlations violate an inequality. Not Bell's inequality, a new one that was derived from those three assumptions I told you about at the beginning. Let me say that again, because it matters. If all three of these are true, that observed events are real and definite, that choices can be made freely, and that influences do not travel faster than light, then the correlations Alice and Bob see must fall within certain bounds. But quantum mechanics predicts they do not. And in proof-of-principle experiments using entangled photons, where the observer is an extremely simple quantum system, the violation was confirmed, just as the theory predicted. So at least one of those three assumptions has to be wrong. At least one of those concrete walls has to crack. And this is not a matter of interpretation anymore. This is a mathematical result backed by experimental data. Let us walk through what happens if you give up each one. Suppose you give up the first assumption. You say, fine, observed events are not necessarily real and definite. Maybe when Charlie sees a result in his lab, it is not an absolute fact about the universe. Maybe it is only a fact relative to Charlie. From Alice's perspective, no definite event occurred until she opened the door. This is essentially what some interpretations of quantum mechanics propose. The many worlds interpretation, for example, says every outcome is equally real but in different branches of reality. There is a branch where Charlie saw spin up and a branch where Charlie saw spin down, and both are real. Neither is more definite than the other until you specify which branch you are asking about. That is logically consistent. But think about what you have just said. You have said that when your friend tells you they saw a specific result, that result is not an absolute fact. It is only a fact in some framework. Reality is not observer independent. There is no single story about what happened. Now suppose instead you give up the second assumption, free choice. You say that Alice and Bob could not have chosen differently. Their measurement choices were predetermined, correlated with the particles in some cosmic conspiracy stretching back to the beginning of the universe. This is called superdeterminism, and most physicists find it deeply unappealing because it means every experiment you have ever done, every choice you have ever made was scripted. You did not choose your measurement settings. The universe chose them for you in just the right way to fake quantum correlations. It is very hard to do science in a universe like that because you can never trust that your experiments are genuinely testing what you think they are testing. And suppose you give up the third locality. You say that what happens in Charlie's laboratory instantly affects what is possible in Debbie's laboratory, no matter how far apart they are. Some interpretations do allow this. Pilot wave theory, for example, involves a kind of instantaneous influence across space. But this sits very uncomfortably with Einstein's relativity, which says the speed of light is a hard limit on causal influences. 3 doors, behind each one is a different version of reality, and at least one door must be open. Nobody gets to walk away and keep all 3 locked. That is what the mathematics says. That is what the experiments confirm. This is the paradox. It is not that quantum mechanics is inconsistent. Quantum mechanics works perfectly. Every prediction it makes about the numbers you will see in the laboratory turns out right. The paradox is about our assumptions, our common sense beliefs about what kind of world we live in. Quantum mechanics is telling us very clearly that our common sense picture is too simple. Something in it is wrong, and it has been wrong the whole time. We just had not pushed hard enough to notice. And the honest answer, the answer any careful physicist will give you, is that we do not know yet which assumption fails. That is the open wound. Each option leads somewhere strange. Each option costs us something we thought was non-negotiable. But I want to leave you with something that makes this even more unsettling, because the trouble does not stop at particles in laboratories. Some theorists have been pushing these ideas further, asking what happens when you apply the same logic to the entire universe. Not a laboratory inside a universe, the universe itself. There is a calculation done in the context of quantum gravity where you try to write down the quantum state of a closed universe. A universe that is not being observed from outside because there is no outside. You are inside it. Everything is inside it. And you try to describe the whole thing objectively from no particular vantage point. The mathematics, using tools developed from studying black holes and using ideas from string theory and holography, produces a shocking result. The entire universe appears to have just a single quantum state. One, not billions, not trillions. One, a universe that is so simple it cannot encode even a single bit of information. Not a 0, not a 1, nothing. Now let that sink in. A universe with stars and galaxies and oceans, and arguments about whether a tomato is a fruit, and the mathematics says the whole thing contains less information than a single coin flip. And yet we look around us and we see complexity everywhere. Stars, galaxies, tables, chairs, people arguing about politics. How can all of that exist in a universe with one state? The possible resolution, and it is still very much under investigation, is that the single state result appears only when you try to describe the universe from no perspective at all, from a view from nowhere. A God's eye view that is not actually any observer's view. When you put an observer inside the universe, when you ask what the universe looks like to someone in it, the complexity returns. The infinite richness comes back. As if the universe needs someone inside it asking questions to have a definite character. Think about what that means. It suggests that the very notion of the state of the universe might not make sense without specifying who is asking. That an objective, observer-independent description of everything might be a fantasy, not because we are bad at measuring, but because that kind of description does not exist even in principle. This is not mysticism. This is not the universe is a dream. This is hard mathematics, pointing at a specific structural feature of quantum gravity. The observer is not a nuisance in the equations. The observer might be a necessary ingredient for the equations to make sense at all. Nobody knows if this is the final answer. The mathematics is still being developed. The implications are still being worked out. We might be decades away from a definitive experiment, but the direction is unmistakable. From the double-slit experiment, through Bell, through Wigner's friend, through these new paradoxes about the structure of the universe itself. Quantum mechanics keeps whispering the same uncomfortable thing. You cannot separate the world from the act of looking at it. The observer is woven into the fabric of reality at a level we do not fully understand. And I find that thrilling, not because I enjoy confusion. I do not. I want answers. But the fact that nature is stranger than we imagined, that she refuses to fit neatly into our categories, that after all these decades she still has surprises hiding in the foundations, that tells me we are not done yet. The best physics is still ahead of us. The deepest questions are still open. 3 assumptions. At least one is wrong. We do not know which, and the answer when we find it will reshape what we mean by the word real. If you had to bet, which of the 3 would you give up? The reality of observed events, the freedom of choice or locality? I am genuinely curious what you would choose, and why.